So now we did that was just a bunch of ways to measure pressure. What I want to do now is think a little bit about the buoyant force. All right. Even this is just going to follow that standard equation we just messed with. Right? I left it up there. Even this, more or less, is going to follow that. So this has to do with the forces that something in water like feels, right? So if I have just a fluid and I put something in it, like the chalk, hey, chalk sinks. There you go. So we want to think about the force something feels while it's in the water. Okay? So let's draw it. Let's see. All righty then. Okay. So we have a thing, water. It has some density rho. Just like we always specify mass in kinematics and forces, we're specifying rho all the time here, the density of the water. And we're going to say, let's imagine that the thing in the water is a nice little cube. Okay? I'm very good at drawing cubes. Most of 7th grade for me was just sitting there drawing cubes on my book. There we go. So we want to say we want the force on the cube. So the buoyant force is the force a fluid applies to a submerged object. And, exactly what submerged means we can get into later. But for now, we're going to say it's just submerged, meaning it's all the way under. It's not on the bottom. It's not sticking up. It's just submerged. So let's get the force on the cube. Total force on cube. Because this will show you where the buoyant force comes from, rather than just believing Archimedes BS. We're going to actually calculate it here. So the sum of the forces in the y, we only really care about the y. Right? So these sides are all perpendicular, so their forces are all in the x direction. So we really care about the pressure force here, the pressure force here, and mg. I'm going to label them in a minute. So this one, we would call this P top, the pressure at the top level against the area A. And we're going to call this the y direction. So pressure at the top pushing down, that'd be negative, minus P top times A. Right? That's a force. So remember, force, pressure times area. Mg is pushing it down. That's just its weight, right? Minus mg, right? But then the only force, the force pushing it up, is P bottom times A, right? Plus P bottom times A. Now you might say P bottom and top, it's all going to cancel. There's no force, but there is, because the whole reason you have a buoyant force is because the pressure in the fluid changes with depth. Right? That's the whole point. Okay? It's pushing down at some pressure here, but it's pushing up at a bigger pressure down here. That's the whole intuitive idea behind the buoyant force. Now we can just ruin your intuition with a bunch of formulas here, but I want to just get that out before this all gets confusing. All we're going to do to calculate it is plug in P top and P bottom using our favorite little equation here. Okay? So I'm going to say it's minus parentheses. Let's write down P top. Okay? Oh dear. Well, let's see. We need to know P atmosphere. Right? So it's whatever's above the column of water plus the density times G times D. So in this case, D is like the depth to the top surface here. So we'll just make up a D there. Right? It's going to cancel out, so don't worry about it. Okay? Rho G D times A. Right? So all we did is substitute our little equation in there. Minus mg. Okay, that's fine. Plus, and now let's substitute in for P bottom. It's P atmosphere. Because if we imagine what's the pressure here, well, we just think of this column of water. We apply our equation. The pressure here is the same as the pressure here. So the fact that the mass is there doesn't affect the pressure along this line, because this is all hydrostatic. Okay, so it's P atmosphere plus rho G, and then D plus, the side length of the cube. Rho G D plus S. So you can see that the bottom is deeper than the top. One's at D and one's at D plus S. So that's total force. So then you look at that, and you want to be good at algebra and just start canceling stuff out. Right? There's a minus P atmosphere. There's a plus P atmosphere. So the atmosphere doesn't affect buoyant force. And you could also look and see the depth doesn't affect buoyant force either. It only cares about the difference in height s. Because right here, you can say this is a minus rho g dA, and here this is a plus rho g dA. Right? So this part of that sum cancels this whole term. Okay? So atmospheric pressure doesn't matter. The depth doesn't matter. The only thing that seems to matter is the thickness or how tall the thing is. Okay. Let's see. I forgot the A, yeah. But I think I put it on. Okay. So let's see what's left. So this whole term's gone, right? So we're left with minus mg to calculate this buoyant force, plus, and let's see what's left here, rho g SA. Rho g SA. Rho g, the side length times the area. And that doesn't look too useful or intuitive. Let's write it in a slightly different form here. Or let's say what these two terms kind of mean. It's the force, the total force it's going to feel is minus mg, its weight. So the weight doesn't go away. Right? The weight's still there. But plus rho, right, g, and what is the surface, or sorry, what is the length s times the area? Is the volume of the cube. Right? The volume of the cube. So rho gv. Okay. So let's think about what these two are. This is basically just the weight of the cube. It's been there the whole time. It didn't cancel. It didn't go away. It's just minus mg. So really this has nothing to do with the cube's weight. Nothing at all to do with the cube's weight. Nothing to do with atmospheric pressure. Nothing to do with how deep it is. Nothing to do with the cube's weight. But this is the buoyant force. And what is it? This is just to make it clear, this is the buoyant force. And let's think about what it is. It's the volume of the cube times the density of the fluid. So what would that be? That would be the mass of the fluid displaced. Right? So V cube times rho fluid equals mass of the fluid displaced. Or the famous way to put it is to see, oh, wait, V cube times rho fluid times G, right, is the weight of the fluid displaced. Weight of fluid displaced. And that's kind of how it's stated as Archimedes' principle and everything. Is whatever amount of fluid you displace, that's the buoyant force that pushes you up. Okay? Okay. Why did the bottom row and G not cancel if the top one did? Oh, I can't follow algebra today. The bottom row and G, oh, they didn't cancel here. So the fact that S was left is you still have rho G SA. So I only canceled this part, the D of the D plus S. I believe is the answer we're looking for. Okay, so now let's see. Let's prove this to ourselves. So it doesn't depend on depth, and it actually is real. Like sometimes people think, is this real? Is this like you're just making this up? So we're going to measure the buoyant force on this, right? So this is a couple of masses, and they weigh, here I'll be like an MD. They weigh 18. Congratulations, you made it down to 18. You weigh 18 now. And now all I'm going to do is float them. Is it still 18? Oh, you still weigh 18. As I'm going to float them in the water. I'm not going to float them. They're going to sink. They're steel, heavy. And they weigh 16 now? 16 what? What do you mean? It's 16. Right? And now they weigh 18 again. Right? So the buoyant force is pushing up and changing the weight. Or not changing the weight. Changing the reading on the scale. Changing the apparent weight. And changing the tension of the string. Right? That'd be a fun question that we could do. What is the tension of the string in this situation? Okay? So it's a real force. It really happens. And the only reason that happened right there, just then, it's exactly the same as this cube, is that you had more force on the bottom, more pressure on the bottom than you did on the top, because of the difference in height in the fluid. So it's nothing magic or fundamental about the fluid. It's just the difference in pressure of a hydrostatic fluid. It's the only reason you get a buoyant force. And the other thing to know is, if we do this real general, it doesn't have to be a cube. Okay? So this result, that it ultimately depends on the volume displaced. This is general, as we say, the volume of the cube here. It doesn't matter what the shape is. The effective area will all come out in the wash if we do it with calculus. I don't recommend it. Okay.